So thank you to Scene for your kind introduction. Those are big shoes to fill. I don't know if I can fill them, but I'll try. So as Tassine mentioned, I did my undergraduate studies here at UC San Diego, and over the course of that, I've had numerous opportunities in different fields, and I've tried to take advantage of as many as I could. Tassine and the Space Grant asked if I could come speak with you guys today and discuss some of the opportunities available to all of you, some of the ones that I took advantage of, and perhaps some of the ones that I wasn't able to that you guys can look into. Any opportunity that you can take is a good one, so if you leave with any message, I hope you leave with that. My title is Oh, the Places You'll Go, a look at the opportunities, obviously a play on Theodore Geisel. So if you don't know who Theodore Geisel is, you probably know him as Dr. Seuss. He's been a major donor to our university, which is why we have Geisel Library that you guys see sitting up on the hill. So if you haven't been to the library yet, because you're still freshmen, you don't need to study till at least 6th or 7th week, you'll get accustomed to the idea of Theodore Geisel and the role he's had with our university. So I thought to explain the opportunities and things that I've been involved with, I just kind of go through a chronological order of my experience. Unfortunately, I get really excited about this stuff and I end up with 90 slides in 45 minutes, so we're not going to be able to cover it all. But the slides will be posted. You guys can go back and look at them at your own time. And then I have my email address on there. You can email me, ask me questions, set up a meeting with me. I'd be happy to help any way that I can. So with that being said, we'll get right into it and start at the beginning. I came here, before we get too far into it, one of my favorite quotes as a little kid was from Dr. Seuss, and it's from his Oh, the Places You'll Go. And essentially it just says you can do anything that you want. So pick what you want to do, dedicate yourself to it, work hard, and you can get there. If you've never read Oh, the Places You'll Go, buy it. You can get it used on Amazon for $3 or $4, and it'll take you 10 minutes. It's worth the read. Before I bore everyone in here to death with the things that I'm passionate about, I wanted to give a couple of take-home messages. So say yes. Again, any opportunity that presents itself, it might not be obvious to you how it relates to your future. I hope that you'll see, as I start going down my path, that things that I started out doing do not really relate at all to what I ended up doing, but were still invaluable to me in my experience in my future. So obviously, it goes without saying, always do your best, but a lot of people think that means when your boss is watching, always do your best, but really you should want to be judged based on what you do when nobody's watching. So put your best foot forward, represent yourself, your family, your school as good as possible, and good things will happen to you. Take opportunities to develop secondary skills. So you might want to get a job in a research lab because you're really passionate about aerospace structures and you just want to know how a wing works and why they design planes the way they do. But what you might not realize is while you're working in that lab, you develop connections, you develop interpersonal skills, you develop all kinds of things that might not have been your primary objective but are still very useful to your future. Stay patient. Nothing happens in a day. Every day is not a milestone. There'll be times where you're in the library till 3 or 4 in the morning and you're like, what am I doing here? Why do I care? And then in 4 years you'll graduate and you'll be like, oh, I have a really high GPA. I had all these awesome experiences. I have all these companies that want to give me jobs. Maybe that's why I did it. So stay patient, work hard. You'll get to where you want to go. And lastly, show initiative. Think outside the box. Look for unique opportunities that maybe aren't as often explored. Take the initiative to follow up on those and try and get yourself some experience. So now we'll start at the beginning for me. I came here in 2010 as a transfer student from a junior college, and I got into school. I wasn't really sure what I wanted to do. I knew I loved airplanes. I knew I was fascinated with them, but I didn't really know what I wanted to do with them. Propulsion, controls, aerodynamics, structures. So I started taking some classes in aerospace structures with Dr. Kosmadka. It's the SE 160A and B sequence. So if you are interested in aerospace structures, you should take those classes. They're great classes and you'll learn more than you ever wanted to know. I went to school with 3 people that went on to Ph.D. program at Stanford, and they took 2 graduate aerospace structures classes at Stanford, and both of them have told me they learned more in Dr. Kosmadka's undergraduate classes than the Stanford classes. So there's a shameless plug for Dr. Kosmadka. Anyway, I started taking these classes. I got really interested in what he was doing, made myself known in the class, showed up on time, sat up front, asked intelligent questions, did my homework and did well, and eventually that led to a position in the lab. So it wasn't exactly that easy. Dr. Kosmadka is a very busy person, and he's also a very powerful person, and he has a line of students outside of his door waiting to get positions in his lab all the time. So what I did is I sat outside of his office waiting for him to come for weeks on end. I sent him email after email, and finally he sent me an email and said, okay, I will give you a job, but you have to leave me alone. I'm going to introduce you to one of my graduate students. You're going to contact him. You can't be emailing me every day asking for a job anymore. So I went into the office, I met with him and his graduate student, and he said, well, this is Eduardo. You'll be working with Eduardo. Basically, whatever he needs, just coordinate with him. And you're free to get started whenever you and Eduardo work out your schedule. So I met with Eduardo after the fact, and he says, yeah, our first project is going to be an F-8 project, which is a maybe 70s-ish fighter plane. If you're not familiar with the F-8, you'll see a picture of it here shortly. But we're doing some testing on an F-8 project. You're going to be involved. So I go home that night. I'm all excited. I start work in the new lab. I just can't think of anything except how exciting it's going to be. We're going to do all this testing on this really cool airframe. I show up to work next day, and I go, okay, what are we starting with? And he hands me a broom. He tells me, well, we have all this really cool testing going on, but we have a lot of visitors in the lab. The lab's kind of a mess. We just got done with the setup, so we need to clean up, we need to sweep, we need to wind cables. He was dead serious. So my first 2 or 3 days I spent just cleaning the lab. So I think the message there is get your foot in the door, do whatever has to be done to finish the project, and you'll earn a lot of respect that way. If you say, oh, I don't sweep floors, I came to engineering school, well, that's fine, you have that right to say that, but you might not get the next opportunity that comes down the line that's something that's more appealing to you. So I swept floors, and I eventually got to the point in the project where I was involved in the testing. What we were really testing is this horizontal stabilizer. So it's responsible for pitch control of the aircraft, if you're not familiar with aerodynamics. And what they were looking at is developing better models to predict how these aircrafts are going to age. So what happened is the Air Force gave us 2 of these horizontal tails, and on your left you'll see the complete horizontal tail mounted to a test fixture. If you don't know what PAL Lab is, it's the big labs in the center of campus that have the 7 sins and the 7 virtues on top of them, and then the labs across the street. So they have these huge walls in there called strongbacks. You can put these massive structures on there, apply a lot of load, and test them. So we had one that we were using to test. We instrumented it with a bunch of strain gauges that we'll talk about in a little bit if you're not familiar with them. But it's essentially a way to measure elongation in a piece of anything, concrete, metal, carbon fiber. The other one was disassembled and used to create finite element models. And then by the testing, we would take the data from our test data, match that to a finite element model, which is an analytical computer model to predict the structural response. And once you've validated that model, you might have 1 million elements in the model, so you can have 1 million different outputs. But until you know that they're correct, you can't trust them to do anything with. So you can put maybe 40 or 50 strain gauges on this, measure the response, and once you can predict the same response for the same applied loads in your model, then you can trust the model everywhere else and maybe learn a lot about the structure in a much cheaper and more efficient manner. So again, I was an undergraduate researcher or research assistant on this project. I don't have a bunch of cool data or pretty plots to show because I was too busy sweeping, but that was basically what the project was about. The other thing that I was more extensively involved with was Eduardo's personal Ph.D. Dissertation research was on detecting damage in laminated composite structures. So who in here knows what a laminated composite structure is? Who knows what carbon fiber is? All right, so you guys have heard of carbon fiber. Basically what they do is they take layers of carbon fiber, they're called plies or lamina, and they laminate them together in different orientations. And we'll get into this a little bit later, but just think of a bunch of layers of carbon fiber stacked together to make whatever structure you want. So Eduardo was trying to look at how these structures break, and he was doing that by monitoring acoustic emissions. So up here is a semi-elliptical section, so you have a half ellipse here, and then some straight legs, and the geometry back here really isn't important other than you can't have it too short or else the waves bounce around as you're trying to monitor the acoustics. So these are the acoustic transducers. They're monitoring for little cracks in the composite. So you can imagine you have this big piece bolted in this load frame. This bottom head stays fixed and this top head moves up. So if you have a semi-elliptical section, as you start to load it, they want to pull apart. Now what happens is you get a lot of stress in this region, which if we have time we'll talk about later. All this stress leads to cracking in the resin that holds all the carbon fiber together. If you monitor those cracking events, you can look for patterns and try and tell when a structure has become damaged to the point where it might not be able to take the load that you want to apply to it. So it's kind of a structural health monitoring or a non-destructive evaluation technique for the structure. So again, here's the specimen, the sensors, and then if we plot some of the data, this would be the cumulative energy measured by one of the acoustic emissions transducers, and the blue line here is the load. So as we increase the load, there's no activity in the specimen at all. And then all of a sudden you get to a crucial load state where the specimen begins to release energy, which is monitored by these acoustic transducers. So you see, you get a little bit of energy, then you apply a little bit more load, something else starts to crack, something else, and then you keep accumulating energy. And you can see as you apply more and more load, you get to a region where the energy accumulates very quickly. So if you can figure out where that is for your given structure, you can detect the damage before it actually happens and potentially do something about it. Think about it in terms of an airplane wing. If you're up there in the air and the pilot knows, hey, this wing is about to break off, maybe he goes into a maneuver that's less severe on the airframe itself, so you have less loading, you can safely land the plane, all of us are happy, and then the mechanics can fix the plane. So that was the crux of his research and the other major project I was involved with as an undergraduate. This is all more of that same research with Eduardo. This is also doing acoustic emission monitoring. So if the last figure was a quasi-static, the load was being applied very slowly. The next one is very dynamic, it's an impact, so instantaneously you put all the energy in the structure rather than very slowly with the quasi-static load. So in this case you have an impact pendulum and you have a composite plate bolted there into the test fixture. So your composite plate, all of your acoustic emissions transducers, and then the impact pendulum. By knowing the mass of the pendulum, the length of the pendulum arm, you can calculate the velocity, and then you can calculate the kinetic energy. So you know how much energy you're imparting in the plate on impact, and that would leave you with a certain level of damage. So again, we're looking at how much energy can these composite materials absorb before they get to a catastrophic level of damage. So if you look at the front, I know the picture is hard to see, but if you look at the plate, it's still hard to see. There's really nothing there. On the back side, you can kind of see the damage. It's about a dime-sized crack. So what they do is, well, there's multiple techniques, but what we did is we stuck them in a big water tank, and it's called a C-scan, and you basically use ultrasonics to peer inside the inside of the composite plate. So think of it kind of like an X-ray for structural components. You send a wave, an ultrasonic wave in one side, it's received on the other side, and basically the frequency of the wave propagating through will tell you how dense the structure is, and therefore you can detect how much damage you've inflicted. So these darker areas reflect more damage. You can see kind of the sensor array overlaid on top of the C-scan. So this is the same plate, this is just zoomed in, so here's the whole plate, just the damage region. This impact head is maybe 1.5 inches in diameter, and the plate's probably about 1 foot by 1 foot to give you an idea of scale. So some of the lessons that I learned in my undergraduate experience is get into a research lab as quickly as you can. Kind of goes without saying, but think about how you're going to do that, formulate a plan, figure out where you want to work, what professors do that research, start taking their classes, start interacting with them and see what opportunities are available. Never think you're above doing any job. I started out sweeping floors, but I ended with the acoustic emission monitoring research. I was building the specimens, I was instrumenting, I was processing data, I was making figures and charts that went into scholarly articles and papers, publications. So these are all good things for graduate school, for employers, for anything that you want to do as an engineer in your future. And then again, always do your best. It's kind of one of my themes. If you're like me and you're not the smartest, you just have to try harder than everyone else. So put your best foot forward, try really hard, and you never know where that might take you. As an undergraduate, once I had been working on the research with Eduardo for a while, I was approached by Dr. Kazmadka and Eduardo to do some research of my own, which I think is a rare opportunity as an undergraduate to have the opportunity to really spearhead research. It wasn't like we need a 12 inch by 12 inch composite plate made, go make it. It was you figure out how to solve this problem. And the problem they presented to me was reinforcing the interlaminar region of composite plates using nanoparticles. So the interlaminar region, if we think back to the composite plate definition where we're taking layers of carbon fiber and stacking them in different orientations, the interface between those layers would be the interlaminar region, so between two layers. And the reason things like this are important is you guys have probably heard, or a lot of you, about the Dreamliner, which is the new Boeing plane. In the next 20, 30 years, it'll be the plane that most of us fly on. The SpaceX Falcon 9, so this is an all-composite rocket that is now being used to transport cargo back and forth to the International Space Station, and hopefully will soon be used to transport astronauts. In case you're wondering what happened to Eduardo, he's one of the head structures guys at SpaceX now, so work hard, you never know where you might get. The Boeing 787, or the Dreamliner, is important because it's the first commercial plane to use the majority of its structural weight in composites. That's interesting for a lot of reasons that I won't bore you guys with, because I'm kind of a nerd about this kind of stuff and some of you might not care. But essentially, these are all composite structures. I said most composite by weight, and that's because the engines and really crucial joints are still made out of titanium, but the primary structures, the wing, the fuselage, thing like that, are almost all carbon, Kevlar, and fiberglass. So this was taken from a presentation that I gave in Maryland last year, so some of it probably doesn't apply or is more advanced than we want to get to today. But what you really want to know is these are all composite. You have a thin composite skin, and then you have to stiffen it somehow. So these are longerons that run along the length of the fuselage and stiffen it. This is an isogrid stiffener that they use in the rocket body on the SpaceX Falcon 9. And when you're flying aircraft, spacecraft, whatever it may be, you have very complex loads. So if you guys have taken any kind of strength of materials or structures class, you know all about loads and how you can combine the loads to get complex stress states. And basically, if you can think about taking like an L-beam and clamping one side and then bending the other, what will happen is you'll develop cracks in this region. And if that L-beam was made out of a composite material, you have all of these layers, and the weak link in all of those layers is in between them, so that's where your cracks are going to form. So what we were trying to do is use nanotubes to reinforce those layers and see if we could increase the strength properties there. So here gives you an idea of a laminate, which is a bunch of layers of composite material stacked together. So the lines would represent the fiber direction. There's a couple different types of fibers and weaves and stuff. We won't really get into that. So for now, we'll just talk about unidirectional, which means all the fibers go in one direction, and then you stack them in different orientations relative to each other to try and tailor the laminate to the specific loads that you're expecting. Again, not that important for our discussion, but if you work in structures, it's something you'll come across later. But we're interested in these regions in between, putting nanotubes in there and trying to form a stronger bond. So right now you have two types of properties. You have the fiber-dominated properties, which are in-plane properties. So if I had a piece of carbon fiber, a sheet of carbon fiber, and I pulled in the fiber direction, it would be very, very strong. But if I pulled in the opposite direction, the only thing holding it together is the matrix, and that's a couple orders of magnitude weaker than the fibers. And same thing in the through thickness direction. So you have all of these plies stacked on top of each other, and they're only bound together by the resin or the matrix. You can use those terms interchangeably. So if you apply a bending load, then they kind of just want to pop apart in between the layers of really strong material. Traditionally, they've put mechanical fasteners in there to try and strengthen these regions. Those work very well at increasing the matrix properties, but they decrease the fiber properties quite a bit because you go around punching holes in your structure everywhere, so you could see the drawback in that. This lower image was an image that I actually took with the help of the Cal IT Nano Engineering department here on campus. So this is one layer of carbon, is the thick line that you see, another layer of carbon, and these are some nanotubes embedded in resin that are bridging the gap. So think of it kind of like a zipper effect that we're going for, where you have two layers and you're trying to bind them together by having nanotubes going perpendicular between. So nanotubes, if you're not familiar, these are carbon nanotubes, and I believe to this day they still have the highest specific strength and stiffness to any material known to man. They're man-made, and basically specific strength and stiffness just means stiffness divided by weight. So on a per pound basis, they're the strongest material that we know of and the stiffest. So if we can introduce these into weak regions, we can see the advantage. A lot of the previous research has focused on doing interlaminar shear improvements with nanotubes. And basically shears, if you have two layers and you wanted to slide them relative to one another, that would be a shearing, whereas tension would be like pulling them apart. So we were interested in tension just because no one's really studied that problem, and we were also interested in doing it in a low-cost manufacturing method so other universities might be able to solve that problem or study that problem. So we use a technique called resin transfer molding, specifically vacuum-assisted resin transfer molding. Again, this isn't too pertinent to our discussion. Just know that you have a bunch of dry fabric in here and a vat of resin, and the pressure differential between the vacuum pump, which is negative 14.7 psi, and the resin pot draws the resin across, and you get resin into your part that way. So you have a couple different ways to introduce the nanotubes in there. You either put them on the dry fabric and then put clean resin in there, or you put the nanotubes into your resin and inject the nanotube doped resin into the part. And we tried both of those methods, and it turned out that the metered spray deposition, or spraying them beforehand, was the more I guess the more favorable approach. It was more consistent, more repeatable. You actually have problems if you put too many nanotubes in a certain region, then you introduce more failure sites. So this was a very repeatable approach. Again, a lot of stuff that's not really relevant to today, but I put in there for completeness if you guys want to go back and see what we did. We are studying these semi-elliptical sections as opposed to ASTM standards. So this is, I believe, the American Society of Test and Measure. They published this huge encyclopedia that you can go in the library and look at, and it will tell you how to test anything you ever wanted to test in your whole life, like the compression strength of water, how you test a composite, how you test concrete steel, your t-shirt, how strong is your t-shirt. It'll tell you everything you want to know. So you can go into these standards and look it up. And they have methods to do this, but none of the methods get pure interlaminar tension, which I'll tell you what that is in just a second. So we developed our own and studied that problem. So interlaminar tension, you can think of if you're looking at this cross-section. This cross-section is formed with taking a bunch of these layers and then stacking them on top of each other around a curved mold. So they're still all layered. You might have 20 layers going across this thickness. And the layers, when you apply this load the way that we're doing it, they want to pull apart from each other. So if I was right here, I'd have like a normal force coming this way and a normal force coming this way, forcing the plies apart. And it's unique to this shape that you have pure interlaminar tension there rather than a combination of tension and shear. So you can really isolate the effects and see how well your nanotubes are working for one loading scenario as opposed to the other. So this just shows you a plot of what the stress distribution is, the interlaminar tension stress through the thickness. So if I'm on this side, then I have this stress. If I'm on this side, then I have this stress. And in the middle, I have the peak stress. So that's where we'd expect failure. This plot shows the radial interlaminar tension stress. So it's again maximum and pure right here in the center. As you move away from that, you get a combination of tension and shear. So what we did for the metered spray deposition is, and I'm quite proud of this because this is what I came up with. We put the nanotubes in isopropyl alcohol. We sonicated them using an ultrasonic mixer, and then we sprayed them on with the pneumatic spray gun. So what we're doing here is we're covering half of it and then spraying the other half so that we can build a control and a reinforced specimen at one time to minimize process variation. So when you remove the cover, you can see we did a pretty good job. These are nice and clean. These are obviously the reinforced with nanotubes. And then we put them in the oven under vacuum. This is a vacuum-assisted resin transfer molding. So if you look carefully, there's a line right here full of epoxy. There's a slight flow front coming across here, which is the epoxy going up over the part. And then you have to look really hard, but underneath this arrow is the outlet port that's hooked up to the vacuum. So again, it's the pressure differential that draws the resin across. After we cured the part, we end up with this, which has half reinforced, half not reinforced. And then we can cut those into two pieces and study the effects of just the nanotubes. So we put some strain gauges on. I promised I would tell you guys what strain gauges were, so I'll do my best in 30 seconds or less. Basically, a strain gauge measures the change in length of something, so you know what the length of your strain gauge is originally. You bond it onto a structure, knowing that length, and then you stretch the structure. When you stretch it, you also stretch the strain gauge, and that changes the resistance inside the strain gauge. You can correlate that change in resistance to the actual mechanical strain or how much elongation it experienced. And the reason that you do that is to determine the stiffness of a material. So if you've taken, has anyone in here taken strength of materials, solid mechanics, SE2? A couple people, so you guys know what I'm talking about. But you apply a load, that's how you can calculate a stress, but then you need to know how much is straining so that you can get a stiffness. So anyway, we put strain gauges here on the apex to see what the stiffness was, and then we loaded them to failure to figure out what the ultimate strength was. And ultimate strength is just what it sounds like. You keep applying load until it breaks, and when it breaks you can say that's how strong it was. So we loaded it up in our familiar test frame, applying a tension transverse to the elliptical apex. And again, as you start to apply the load, the apex well, I shouldn't say the apex, the ellipse opens up, so your semi-major axis is decreasing and your minor is increasing, and right before failure it looks something like this. The arrows on here are to depict the interlaminar tension, so again the plies are trying to pull away from each other in those directions. If you made a whole bunch of these specimens at varying concentrations of nanoparticles, you would end up with a plot that looks like this, where the red line is no nanoparticles, and the black line is varying concentrations by percent weight. Yes, these are really percents. I didn't forget to multiply by 100, but they're just very small numbers because you have so much material and just a little bit of carbon nanotube. So you can see that the noise of the system is around 3%, so with no nanotubes, just spraying alcohol in the fiber, we still measured a 3% gain in strength, which is obviously not real. It's just because our load cell isn't infinitely precise, so at some point you're going to get noise in your loads. But by the time we get up here, we can say with comfort that we're experiencing 17 or 18% gains in the interlaminar tension strength of the materials at ratios between 0.1 and 0.25% concentration nanoparticles. And then a very interesting thing happens as you add more and more, you get less and less return. So nanotubes range between $5 or $10 a gram to $5,000 or $10,000 a gram. So the high quality ones are the ones that we use to do this. So you think, well, if I just put $10,000 in, that has to be twice as good as 5,000, right? And the answer would be no. So think through what you're doing and why things like that might happen when you start doing research of your own. So I won't bore you with all the rest of the details. We'll move on to maybe some topics other people are interested in. But these are plots of the stress versus strain. So the slope of this line basically gives you the stiffness. So you can see that the stiffness had a negligible impact. The nanotubes had a negligible impact on the stiffness of the parts. The last thing that I kind of want to point out to give a visual representation of the strengthening is we showed earlier that the stress should have been maximum at the midline. So if there's no reinforcement, this white line is actually paper that we shoved into the delaminated regions under load so that we could mark where they failed at. So this one happens right in the middle, but if you look at these ones that have been reinforced, it happens just outside of the nano-reinforced zone. So the middle third amount of plies were reinforced, so you know that this is outside of the center where you have the peak stresses, and what that means is we made it so strong that even though the stress is lower here, the material is that much weaker that that's going to be where the weak point is in the chain, and that's where it fails at. We tested the in-plane properties to see that we didn't have any of the problems that the conventional mechanical fastening methods had, and we cut those out of these specimens so we could be sure that we were comparing apples to apples. We know interlaminar tension, we increased the strength, but what do we do to the in-plane properties? And we tested them, and I'm here to tell you that the tests were good. So I won't bore you again with all the numbers, but it was favorable. If anything, it increased the properties. So now we found a way with a negligible weight, a lot of cost, which is the drawback, to increase the out-of-plane and the in-plane properties. So the lessons, once you've made it into research, do your best. Again, you guys see my theme here. You never know when you may get your own project, so I started out just helping other people. I wanted to work in the job in the lab because I was passionate. I also needed a job, so I got paid, got a bunch of cool experience, and then it led me to my own project. And then never say never is because I came here as a transfer student and I could not wait to finish school. I never thought I would go to graduate school a day in my life until I started doing research. So I got into the lab, I got involved, I figured out this is really cool stuff, but unfortunately I can't convince a company to give me a $10 million budget to research this stuff when I have a bachelor's degree. So if you want to do research, you'll probably need an advanced degree. There's exceptions to every rule, but I got into it, I got so passionate about research that I just couldn't stop, and if you asked me 5 years ago if I had been in graduate school, I would have laughed at you, and now here I am in my third year of the Ph.D. program. So never say never. Composite UAV design and fabrication. This is kind of what led me to aerospace engineering. I love planes. I grew up by an Air Force base. I used to make my dad stop on the way home so that we could go walk through and look at all the planes. And designing and fabricating planes are something that I'm extremely passionate about. So in order to get some experience, I joined the UCSD AUVSI. This is a student-run organization. It's the Association for Unmanned Vehicle Systems International, which is a real professional organization that puts on all these student events, as well as professional events. throughout the year. So we're a student organization. We do have a faculty advisor, but he takes a very hands-off approach. So we do all the fundraising, we do all the design, the planning, analysis, plan the trips, ship the plane, everything is all done by us. So we're not a unique student organization in that every student organization has lots of opportunity for you guys to get involved and take a leadership role. We are unique in that we build the only autonomous airplanes on campus that I'm aware of, so if you're interested in that, then you got to come see us. But if you're interested in something else, there's an organization for you. At the end of the presentation, I have a list of some of the ones that I'm familiar with, as well as a link to find maybe some that meet what you're interested in a little bit better. So this is a very multidisciplinary team. No matter what major you are, unless you're maybe poli-sci, then we have someone on our team or has been on the team from your major. Every math, science, or engineer we have on the team or have had on the team, and they're all valuable to us. So that's my shameless plug. If you're interested, our first general body meeting is next week. You can talk to me afterwards. So our mission is to build an aircraft capable of autonomous takeoff, navigation, and landing. We use auto-generated search paths to fly through waypoints that are assigned by the computer in real time. And this is all software that we develop in-house. We don't have any commercial software on board that does any of this for us. So we have an excellent team of software engineers, computer science engineers, electrical engineers. And then the stuff that I do mostly is the aircraft fabrication itself. So every year we go in June to a 3-day competition in Maryland. It's a really cool experience. I haven't got to experience it myself because it happens to be in finals week, internships, graduation, all these fun things. But if you can figure out how to work in your schedule, I've heard nothing but great things from everyone that's been. We divide our team into 4 groups, which again I won't bore you too much with. Just to say that I'm the airframe team. We work closely with all the other teams really, but mechatronics is responsible for instrumenting the payload, kind of adapting our ideas. So for instance, we have a camera to do imagery. Well, how do you point the camera where you want it to go? The mechatronics team takes care of that. They design and fabricate a gimbal that can point it in any direction we tell them we want it to. So embedded team develops all the hardware to implement the software's algorithms. So software has algorithms that look at images and capture what they are, and I'll talk about that in just a little bit. The autonomous flight portion, sending data down through a downlink, all of those things are things that software challenges that are very interesting, very applicable to industry, and things that a lot of past members have gotten very cool jobs for having on their resume. Here's a picture of our current airframe. It's Falco 3. This is a 3rd rendition of the same airframe we've been using for the last 5 to 7 years off and on. So it's about a 10-foot wingspan plane, 55-pound gross takeoff weight. So you're not going to go flying on it, but it's not a small plane either. It would hurt someone if it fell out of the sky. So it's pretty cool to work on. Before we actually build it, there's a lot of analysis and stuff that go into it. So these are finite element models. When I was telling you guys earlier about the models that we were making of the horizontal stabilizer, this is what I was talking about. So this is an all composite fuselage, and what we're looking at on the contour plot is the maximum failure index. So you can basically make these computer models and tell it, here's all the loads that I want to apply to the structure. Tell me how likely it is that the structure is going to fail. And oh yeah, by the way, where's that going to happen at? So right here is where it's going to happen at. And you say that's kind of a weird spot for it to happen at. Well, if I could rotate this 90 degrees, you wouldn't think that, because we have a big hole cut right here for our camera to point through. So it makes sense. You have a big hole, you have a lot of stress concentrations, it's likely to fail there. Same idea. Here's an analysis of our landing gear. So you could imagine the wheels would go on right here. You land, you probably can't see these little green arrows, but those are like force vectors coming into the landing gear from contact with the ground, and then you get some kind of stress in the part. So how much stress do we have, and is the layup or the composite part that we've designed strong enough to take those in the worst case scenario? So before any fabrication gets done, all of this modeling and analysis is done. And again, these are things that real world companies do. If you go to NASA, to Boeing, to General Atomics, they don't just say, well, take your best guess. I know you've done some hand calculations in the past and see if this plane's going to fly or not. There's a lot of analysis that goes on. So these are all very valuable skills. And again, we're not unique and we're the only team that does this. Most of the project-based teams on campus do this, so get involved. There's an opportunity for you on every project to do anything that you're interested in, and it looks really, really good in job interviews and on your resume. So here's a couple pictures of us actually fabricating. We design and build our own tooling. If you're familiar with shaping surfboards at all, what we do is we take foam, we shape it into what we want, we put a hard resin on top of it, and then we build a layup on top of it. So you can think of the foam as like a metal plug, and then once you lay up and you pull that off, you now have a female tool, which is a cavity that you can lay up on. So you want a female tool because you want the outside of your part to be nice and smooth and pretty. So you make these cavity molds that allow that to happen. The green film is just a bagging material to apply pressure to the part to get high quality parts, and then the yellow lines are the vacuum tubes. So you can see here, this is our quote-unquote all composite layup. And I say quote-unquote because you guys are astute enough to say, hey, there's balsa wood in there, and that's not a composite. You could argue with material scientists. They'll probably tell you that wood is a composite because you have sap and you have grains and you have all these things. But on a microscopic level, you'd be right. This isn't really for strength. This is to increase the inertia. So again, if you've taken any structural classes, an I-beam, this is the composite equivalent of an I-beam. You're trying to move the strongest parts furthest away from the bending axis to increase the strength in them. So there's our fuselage, and then bond the two halves together, put some wings on it and a tail, and before you know it, you're ready to go flying. So this is our next generation airframe, another slight shameless plug. We've done all this stuff for Falco in the past, but we're doing all this stuff again for Andros currently. So we have a general concept of what we want the plane to look like, but nothing is hammered out yet. So if you're interested in designing planes and whatnot, come talk to me, look up AUVSI. There's another organization on campus, AIAA DBF, and they do great work also. So if you're interested in planes, look us up. So about what the rest of the team does, that was kind of all about airframe and what I know most about. I don't really know a whole lot about what they do. I'm not smart enough to understand all of it, but I was smart enough to ask them to put together a couple slides that I could share with you. So this is from our software and embedded teams, and this is a picture of the desert floor that doesn't look very interesting except for this little object right here. And this is a picture that was actually taken by our image system autonomously in flight. And it then zooms in and say, hey, what's that strange thing that we see there on the desert? And it turns out it's a black rectangle with a yellow D on top of it. And it sounds very simple to you. Why would we ever want a plane to do that? But what about when you're on the other side of the world? You'd like it to just tell you, hey, we saw this target, this is where it's at, and this is what it looks like. And that's what the software that our team has developed is capable of doing. So this is a image that's been stitched together, the competition field from last year. So as we're flying, we're taking a bunch of still images. And then again, the software team has stitched together all these images to make a coherent map of the airfield. You can see that we did have some problems with our technology last year, so this isn't quite as coherent as the map of the desert. The desert's a little bit easier. You don't have quite as much contrast from what I understand, so it makes it a lot easier to process. But we were able to pick up some targets still in the grass way down here somewhere. I don't know if these are the targets or they just look like targets to me standing here. But essentially you stitch together this map, you have algorithms search through it, and then you can locate the targets. Optical character recognition is how they do it. They spot something weird, and then they do what's called segmentation, where you try and break it into binary information for a digital processor, i.e. a computer, to be able to look at and tell you what's going on. So they're interested in shapes and letters, and then what's not on here is colors. So our system's capable of telling you all of those things. This just kind of summarizes all that. Find a feature, segment it, compare it to known shapes, known letters, and known colors, and see what it's supposed to be. And then you can verify this either by running more images of the same GPS coordinates or by manual inspection. So here's a picture of our team from last year. So these are just the people that showed up every week and on the day that we needed to get the picture taken. But most student orgs, you're not required to go every week. We understand that school is very important. So do your best, be accountable, but at the same time, join one and put forth as much effort as you can, because you'll definitely get back way more than you put in. So I know that I'm talking way too much and we're not going to make it very far. These are some of the lessons that I learned. The one that I really want to highlight is that this is the most noticed point on my resume. Whenever I go to job fairs, recruiters, I have interviews, the first thing that 90% of them ask me is about my experience in my extracurricular AUVSI activities. So I had a high GPA, I have lab experience, and they don't care. They want to know what I did here. So get involved. This has led into my own research. I want to get into the NASA stuff a little bit, so I won't talk too much about it, but basically Anthony and Spencer and I are all building this plane, and it's for structural health monitoring. So if you want to monitor the health of composite flight structures, if you want to know how well your structures are doing in real time, then you have to have a structure to fly. So that's what this is. This is our plane that we're building. We'll put a bunch of different wings on there with different levels of damage and try and detect the damage and then predict how the damage is going to evolve with time. So this is our fabrication progress so far, and now we'll get into the NASA stuff that you guys are maybe more interested in. So I went to NASA in the summer of 2013. I had the opportunity to take an internship there at the Dryden Flight Research Center. And what we were working on was active load redistribution, which basically, think about a wing in flight. You're generating a lifting load, and there's some kind of distribution over the wing. You'll see what that looks like in a second, but for a conventional wing, it's elliptical shape, is the optimal shape. And the wings are optimized for a particular flight condition, but what happens when you're flying in any condition other than that? And that's what we were interested in. We were interested in making wings that could morph themselves into shapes that would be optimized over a wide wide range of the flight envelope. So current wings take control surfaces are the surfaces on the trailing edge of the wing, so on the end of the wing that basically make the plane maneuver. So traditionally you have a flap and an aileron, and the flaps would be these segments here, and they're for generating high lift at low speed. So if you're on a plane, you're taking off and landing, you see those big things come down from the end of the wing. Those are your flaps. The ailerons aren't really shown in this picture, but they're out towards the tips, and those basically roll the aircraft to aid in the turning, or do a majority of the turning. And so the problem with those is they're very large, and you can just give one big input across a large section of the wing. But what happens if you can localize that input more? Maybe you can tailor it to your flight conditions. So what we worked on, and what I'll show you in the next 10 minutes, is the segmented trailing edge design, which is taking the main control surfaces and segmenting them into a bunch of smaller pieces. And if you expand on that concept, you'll get a conformal control surface, which is basically a flexible skin wrapped over these segmented trailing edges. Oops. So again, just a larger, now you've incorporated the whole control surface, and eventually the goal is to get into these flexible wing concepts that can entirely morph themselves to a given flight configuration in real time. So those are kind of the objectives. Build a small UAS, or perhaps modify an existing UAS as unmanned aerial system, so small aircraft, to have these segmented control surface wings. Use real-time information, in this case strain, to monitor the structural state, decide if that's a favorable or unfavorable configuration, and then move the segments accordingly. In order to do this, we had to develop aerodynamic load models and then plug those into structural models to predict the response and decide what was favorable and not favorable for the development of our controller. And then, of course, implement all this to actually control them in flight. So again, flaps close to the plane, so your fuselage would be over here. This is the wingtip. They have unnecessary structural and aerodynamic loads. You deflect them, you get large control inputs. That's not such a good thing. Maybe you want higher resolution of control inputs. You want to be able to localize them. So what we did is we took those main segments and we made a bunch of small pieces, and that way we can deflect them in any configuration that we chose. So this is interesting for a lot of reasons, mainly to optimize your wing shape over the entire flight envelope, and eventually work your way up to these flexible wing concepts that can morph into different shapes in real time. This enabling technology was this fiber optic sensing system, or FOSS, and then the CFOSS is because this is the compact rendition so that we can fit it in a small UAV. It's about 6 inches by 6 inches by 12 inches to give you a scope. And basically what it does is it uses fiber optic strain sensors. So I told you what an electric resistance strain gauge is. Now these are fiber optics. It's a fiber optic cable, just like you might get your cable or internet through. But what they do is they etch these gratings on there, and then you shoot a laser down it, and the spacing of these gratings determines how, the spacing of the gratings determines the wavelength of light that you can expect to be reflected back to you when you shine the laser down it. So if you bond these grated fibers to a structure and then strain the structure, it in turn strains the fiber, which makes the grating spacing change. And if you monitor the wavelength coming back, you can tell how much your structure is actually strained. So for a couple grams, the fibers are about the diameter of a human hair, so a couple grams you can get a couple thousand sensors. Weight's a big deal in aerospace. So 1,000 sensors of electric resistance strain gauges might cost you 10 pounds of weight penalty, where this is on the order of a couple grams. This is the aircraft that we used. You can see our tape lines where we planned on putting the sensors. So we had this aircraft given to us, but it had just the normal flap and ailerons. We put all these fibers onto them to be able to measure the structural response as we started to change the wings. So here's a good shot of the wings. This is a stock wing for that aircraft, and this is what we ended up with. So you can see that there's a bunch of small segments, each that have their own actuator on there, and then there's fibers on the top and bottom to tell us if we're in a favorable or unfavorable configuration. And we were judging that based on structural response, because we were a team of structural engineers, but the aerodynamics would probably come in and say, well, you guys bonded all these things to the bottom, and they would be right. So the next generation of the project is working on internalizing all these components so you don't have so much drag created from introducing all these segments. But essentially we have all these segments, we put them on the plane, we mounted the fiber optic system in the canoe here on the bottom. We went through all of our models. So this red line would be like the conventional control surface wings. That's the elliptical distribution. So this is span-wise. If I had my arms out like this, that would be the wingspan. And if I plotted a line across that, this is what the lift looks like from tip to tip. And as you start moving these segments around, you can play around with the distribution, and that in turn plays around with the structural loads that you have in there. So you might not need as much structural weight because you might be able to just shift the loads when you get into a high load environment such that your structure can take it at different parts of your structure can help carry the load differently. So you're basically just redistributing it into a more intelligent fashion, just instead of the one configuration that the normal wings give you. So again, we took those loads, put them into structural models, measure the response. Once we had convinced everyone at NASA that we weren't going to crash this and we weren't going to kill anyone, after lots of paperwork and presentations, we finally got to fly. So I'm going to skip the video. Well, it's only a short video. I don't have a flight video, unfortunately, but this video will show you what I call mimicked conventional control, and that's kind of what's important. Is what we did is we digitally linked the servos. So if you pay really close attention, you can see this segment moving, and really all of these inner 21s are moving, but because of the poor resolution you can't tell. The pilot will flip a switch and all of a sudden they're all linked together, so you can mimic the aileron and you can mimic the flap. That way we can test the difference between our control algorithm and the conventional aircraft in real time without ever landing, without changing wings, with eliminating all of the process variation basically. So you can't really see, but again, this is moving, and it's moving because I'm straining that wing. So as I increase or decrease the strain, all the segments on the wing will move to try and find the optimal configuration. So what we did is we flew this. I don't know how to stop the video. We might have to just watch it. All right, so we flew this using the mimicked conventional control and the segmented control surface, which was our algorithm. We did all of these different flight maneuvers, which I won't bore you with what those all mean, but basically we just put the aircraft through any flight maneuver you could think of encountering in a normal flight. And we plotted the acceleration, how quickly the aircraft was moving up and down. So that's the green signal, and then the white signal, it's kind of hard to see, would be if you applied a time averaging filter to that just to kind of clean up some of the noise in the data. We calculated the wingtip deflection or displacement by integrating the strain along the span, and that's the blue line, with the orange line being the same time average filter. And if you pull those two signals off and look at them on the same plot, you see a very strong correlation. So the more it bounces around up and down, the more your wingtip deflects in the upward direction. So what was interesting is no matter what, well, we normalized the data such that no matter what your acceleration was, you're looking at the wingtip response normalized to that acceleration. So if you have 4 Gs of acceleration, then you basically divide your displacement by 4, and that way you can compare on a one-to-one basis as you go through different flight maneuvers that have different levels of load. And you can see when we turn the control system on, all of a sudden our normalized wingtip deflection goes way down. So we did about 2 minutes of maneuvers with the control system off in the mimicked conventional control. Flipped it on, let it fly for 5 minutes, repeating all the same maneuvers over and over again, and then turned it back on for the last 3 minutes. And you can see across the board we had a reduction in the tip deflection. So we were finding the optimal, maybe not optimal, but a better configuration. Optimal is kind of in the eye of the beholder, and maybe you could develop a better one. Just kind of driving the point home, if we look at one point in time, this would be without the control algorithm on, would be the white and the gray lines. So this is strain on the top plot and displacement on the bottom. You turn them on, and all of a sudden you have a lower strain, a lower displacement for the exact same flight condition. So the lessons learned, this project was really self-motivated. There wasn't a lot of oversight. My mentor there was extremely busy, so he kind of gave me as much rope as I wanted. And fortunately I didn't hang myself and I got to go back. So it's important to be motivated. developed a lot of skills working in a team, people from various backgrounds, various skills, various schools, and then building relationships. I made so many relationships there. Tomorrow I'm going back to NASA to test some stuff that has really nothing to do with what they're interested in, but they thought I was an alright person and said, hey, you can come back because that's what you're interested in, and we'll let you use our $100,000 equipment to test your own research. So build those relationships, be nice, put your best foot forward. Structural health monitoring is my current research interest. I don't have time to get into it, but I'd love to talk to you about it sometime. If you're at all interested, send me an email, we'll get together. I do want to skip ahead in the remaining couple minutes I have to the opportunity section. And these slides, I believe, will be posted, correct? So you guys can refer back to not only these, but the opportunities. Here's my lesson from grad school, and unfortunately you guys are going to have to watch it. So far that's all I have for you, but I'll keep you guys posted. The opportunities, here's the engineering organization with project teams. So you can go to this link, you can find this exact same diagram, and you can also find a lot more that aren't project related. So project related means you're actually going to build something, you're going to have a tangible result, but that doesn't mean it's the only valuable organization on campus. So these are just the list that I pulled out, but there's a lot more. This is by no means all inclusive. But think of what you want to do and you can do it. Do you want to build a canoe out of concrete? A car powered by chemical reaction, or maybe just solar power or electricity, autonomous airplane, airplane that has a unique design challenge. IEEE is the electrical engineering. They do all kinds of crazy circuit designs that I couldn't begin to try and explain to you guys. There's 2 different rocket clubs on campus. You can maybe find some people in here in the audience and ask why we need 2 and why they don't get along. And you can go to both and figure out which one you want to be on. So anyway, this is a really good link. If you go to this link, you can find all of these links, which will take you directly to their organization's website. Internships, if you're not familiar with Port Triton, Google it. It's where the companies that contact the university, they go through the Career Services Center, who manages this Port Triton, which basically posts all the opportunities on there. DCAF is a job fair that if you're not familiar with it and you're an engineering major, you'll be familiar with it come February. It's a major event on campus. Somewhere between like 70 and 100 companies come looking for engineers from UCSD. So it's a good chance to show them all those extracurriculars you've been working on and why they should hire you and not the 100 classmates that have all the same courses that you have. So differentiate yourself, make yourself a valuable commodity to these companies or to prospective graduate schools, and you'll be very happy that you did in 3 or 4 years. Student Services Center, they host resume and interview workshops. If you haven't gotten emails from them, contact them, ask them when they are. They're located right in the center of campus, just off Library Walk, just slightly west of the Price Center, I guess southwest. So ask someone where it's at. These workshops are invaluable. You can get critique on your resume, you can do mock interviews, you can get a lot of practice, a lot of positive feedback without so much pressure on, if I don't do well, no one's ever going to hire me. Employer websites, obviously, if you're interested in a certain company, go on their website, stalk their website, wait until they put up a job that's perfect for you. Use keywords in your resume that match what the description says so that when a recruiter that has no technical background is looking through your resume, they can say, well, I can check this box, and this box. They meet all the requirements of what the technical person was looking for. Let me pass this resume on to the technical person. Last shameless plug for the day, I promise. NASA OSSI, it's the one-stop shopping initiative for NASA. So you can go on there, you can apply for scholarships, fellowships, internships. You fill out one broad application, you just check a bunch of boxes what you're interested in, and if you're qualified, they'll contact you. So it's been very good to me. All of my money for research and personal living comes from this website right now, so I have to give them a plug. Research labs, most professors conduct research, as you know. There are some associate professors that do not. So get involved, take classes with these professors, find out what they do, make yourself known to them, and then talk to them. If you go in during 10th week and say, well, I haven't passed any of your midterms, and I don't turn in most of my homework, but I think what you do is fascinating, you're probably not going to get a job. So be on time, sit in front, pay attention, and things will work out for you. Some opportunities are even paid, so you can quit your job and focus on doing things that will enhance your future. Tips for success, you guys are probably already sick of me talking about these, so I will skip over them and just do a couple thank yous to my mentor and professor here, my faculty advisor, Dr. John Kosmatka, who's also the director of the Space Grant. Dr. Lance Richards, who was my first mentor at NASA Dryden when I went the summer 2013. Mr. Francisco Pena, who was my mentor in 2014 and who welcomes me back when I call him and say, hey, can I come tomorrow and take up 2 days of your time? So thank you, Mr. Pena. And then of course Tessine and Rebecca have been so good to me over the last couple of years, not only organizing events such as this and giving me the opportunity to talk to you guys, but also helping me when I have questions, helping me sort out who's going to pay for my tuition, helping me figure out how I'm supposed to get the money from this scholarship. So they've been invaluable. They're always so helpful, and they're in EBU too. If you guys don't know where they're at, go find them because they're a very valuable resource. There's a bunch of people at NASA, Dryden/Armstrong that have been helpful to me, and I don't want to leave anyone out, but I couldn't fit them all. It would take too many slides. So these four in particular have been crucial to my work that I did there, as well as the research that I continue to do down here. So I just wanted to give them a mention. And of course, you don't want to bite the hand that feeds you. So thank you for everyone that has given money to support my research throughout the years. Currently, the Aeronautics Research Mission Directorate, Aeronautics Academy has sponsored my 2 summer programs, and of course, the California Space Grant helped with all of my undergraduate research and some of my graduate research, so thank them as well. The last quote that I'll get to is basically saying, again, Theodore Geisel, Dr. Seuss, find your mountain, pick what mountain you're interested in, figure out how to start climbing it. It's going to be a long climb, but just keep going up and you'll make it. So I encourage you to get the book, Oh the Places You'll Go. You can find all these great quotes and more. And I know we're out of time, but if anyone has questions, I'm happy to answer them.